Hello students, welcome back. So today we are going to discuss the lecture number 5 of our chapter, that is the periodic classification of elements. What we have discussed in our previous lecture, that is the periodic trends about the valence electrons, valencies, atomic radii as well as the ionic radii. And today we are going to continue the periodic trend and the properties, and we are going to see that is some of the ionization energies and electronegativity, electron gain enthalpies and the nature of oxides that the element form on reacting with the oxygen. So let us see the contents that are ionization energy, which is represented by IE, electron affinity, or we can say that the electron gain enthalpy, and I am also going to tell you what is the difference between electron affinity as well as the electron gain enthalpy and electronegativity. And at last we are going to see that what is the nature of oxides and how it will be affected as we move across the period or down the group. So let us start with the first topic, that is the ionization energy. So students, what is ionization energy? Ionization energy is the amount of energy that is required to remove an electron from the outermost shell of an atom which is present in its gaseous state, and it is also isolated from other atoms. So we can see that the ionization of energy of an element is defined as the amount of energy which is required. So it is the energy that we have to give to particular atom of an element so that it removes an electron. The amount of energy that is required to remove an electron from an isolated gaseous atom. It simply means that an atom should be present in the gaseous state and it is not in conjunction or it is not in association with any other atom. It should be a isolated atom of that element. So after the removal of an electron, what happens? The atom would automatically change into ion, and we call that ion as a cation or a positive ion, so resulting in the formation of a positive ion. Here you can see this. Just for an example, A is what? A is an element, or I can say it is an atom of any element. And if I provide some kind of energy, so what happens? It will convert into A plus, that is the cation, and it will remove one electron. So the amount of energy that it required to remove one electron from the outermost shell of an atom, this particular energy is termed as the ionization energy. It can also be written as delta IH. It simply means that delta is what? Change in the energy, and H stands for the enthalpy. Or simply you can say that it is used for the energy. So here you can represent ionization energy as IE or as delta IH. So let us see some of the examples. Here you can see that is the magnesium atom, in which there are total 12, that is 2, 8, 2 electrons are present. So when we give the energy to this magnesium atom, one electron being removed and it converts into the Mg plus 1 ion. So here it converts into Mg plus ion, that is its electronic configuration will be 2, 8, 1, and the electron being removed. You can simply see only one electron in its outermost shell, and here you can see that there are 2 electrons in its outermost shell. But remember students, the magnesium should be present in the gaseous state for the removal of electron. Then only you will call this particular kind of energy as an ionization energy. If the electron would have removed from the solid state, the particular kind of energy cannot be defined as an ionization energy. Remember this one point, that it should be in the gaseous state. Okay, now students, moving into another, that is the successive ionization energy. So what happens if we remove single electron from an atom? If we remove single electron from any atom, it will convert into M plus and one electron being removed. So this particular energy is termed as the ionization energy first. Now the successive ionization energy, it means what? That I am removing one more electron from this particular cation. So on removing one electron from this particular cation, we get what? M plus 2 and one electron being removed. So here this particular energy is termed as the ionization energy 2. It simply means that it is the removal of an electron from the cation, which is formed by the removal of one electron from the metal which is present in the gaseous state. So similarly we get the third ionization energy as the removal of an electron from the m+2 in the gaseous state. Here m represents what? M is representing any element. So just for an example, you can see that, just for an example, if I talk about magnesium in the gaseous state. So if I provide some kind of energy, that energy will be termed as ionization energy, and it will convert into Mg plus and one electron being removed. So this first energy that I gave to remove an electron, it is termed as the ionization energy. Now if I remove one electron from what? From the Mg plus ion which is present in the gaseous state. So if I remove one electron from this Mg plus, so this particular energy will be termed as ionization energy second, and the Mg plus will convert into Mg plus 2 in the gaseous state. It is also in the gaseous state, and one electron being removed. Now what happened if we remove also one electron from this Mg plus 2 ion which is present in the gaseous state? So if I remove any further electron from this Mg plus 2 ion, this energy will be termed as ionization energy 3. So here it will convert into Mg plus 3 which is in the gaseous state, and there is a removal of electron. So students, this is very much important for you to note that in all these three cases the electronic configuration for magnesium is 2, 8, 2. That is, in the first shell it has 2 electrons, in the second shell it has 8 electrons, and in the third shell it has 2 electrons. So if I remove one electron from this magnesium, it will convert into Mg plus, whose electronic configuration is 2, 8, 1. So I am writing here 2, 8, 1. It simply means that it has one electron in its outermost shell. So if I remove this particular one electron, the electronic configuration of Mg plus 2 would be 2, 8. So here the electronic configuration of Mg plus 2 is what? That is 2, 8. So if I supply some kind of energy to remove an electron from its outermost shell, now its outermost shell is the second shell. So we get what? That is 2, 7, which is the electronic configuration of Mg plus 3. So students, here you see and note that in this particular case, say about for this Mg plus 2, it is having what? It is having number of protons and number of electrons is equals to 12. Alright students, so the force of attraction between the nucleus and the electrons is certain. But what happens when an electron is removed? So here the number of protons is greater than the number of electrons, or you can say that the number of electron is less than the number of proton in Mg plus. And what is the difference? The difference is 1. So the electrostatic force of attraction between the nucleus and electron is now increased. So what happens when we remove one electron from this particular cation? We require more amount of energy to remove that particular electron. Same in the case here, you can see that it contains, Mg plus contains what? Mg plus here contains total number of 12 protons, while there is only 11 electrons. So the force of attraction between the 12 protons and 11 electrons is somewhat higher than in the case of magnesium atom. Also you can see in the case of Mg plus 2, it contains what? It contains 12 protons while only 10 electrons. So here in this case, the force of attraction or the nuclear force of attraction between the protons and the electrons is the highest in all these three cases. So here now you understand students that to remove an electron from a cation would require more amount of energy than to remove an electron from the atom. So here the trend for the successive ionization energy is that when we remove an electron from an atom, it is termed as ionization energy 1. When we remove an extra electron from the cation, it is termed as ionization energy 2 and ionization energy 3 and ionization energy 4 respectively, and so on. So here you get this particular trend, that is the successive ionization energies are always greater. So here you can also see that if particular atom encounters the stable noble gas configuration, that is 2, 8 for Mg plus 2. So if we want to remove one extra electron from this particular Mg plus 2, we would require a hell lot of energy to do that kind of work. So in this particular case, just for an example for Mg, if I am writing here for Mg, the ionization energy 1 is less than the ionization energy 2, and which is very less than the ionization energy 3. So remember students, the successive ionization energies keeps on increasing. So students, now moving into another, that is the units of ionization energy. So what is the unit of ionization energy? We can take energy's unit is simply joules or calories. But for an example students, if we are not taking a single student, if we are taking 1 mole of atoms, then the amount of energy we required is in the kilojoules. So the unit will be what? That is the kilojoules per mole, or you can either use that kilocalories per mole, or you can either use the electron volt per atom. Remember students, this particular case here, that is the electron volt per atom, it is also the unit of energy. So what is the relation between kilojoules and electron volt? So here you see that is 1 electron volt per atom is equal to, that is 96.49 kilojoules per mole, which is also equal to 23.06 kilocalories per mole. And remember this particular case, that is 1 electron volt per atom is equal to 1.602 into 10 to the power minus 19 joules per atom. So here we have seen the units of ionization energy. So let us now move into some of the trends across the period or across the group in a periodic table. So moving, we will see that this particular moving and we have seen that this particular picture, in this particular picture there are bars of the elements which is giving us the ionization energy. So here you can see that the bar for hydrogen is much higher than that of the lithium, sodium and potassium. It simply means that the ionization energy is higher for hydrogen in this particular group, that is hydrogen, lithium, sodium, potassium, rubidium and cesium. You can see that there are the steps. So these are the steps as we move from bottom to the top in a group. So here the least amount of ionization energy for the alkali metals is given for the cesium, and rubidium has higher amount of ionization energy, and potassium is more, and sodium is also having some kind of more energy, and lithium is having the greater energy in the case of alkali metals. So you have already seen, you can also see in these cases also, that is the first member of any group is having the higher amount of ionization energy, and as we move down in a group, the ionization energy keeps on decreasing. So why it is happening? It is simply happening students just because if I say this is the nucleus, these are what? These are the shells that are present in an atom. So if I talk about this particular case which is having only one shell, so here the electron is represented with this particular blue dot. I am simply representing the outermost electron student. So here the distance between the nucleus as well as the electron is very much less. So the force of attraction between the electron and the nucleus would be much higher. So it would become so much difficult to remove this particular electron. While in the case of this bigger atomic size, just for an example, I am representing here an atom, only the outermost shell atom. Remember students, I am not representing any other electrons in the inner shells. So here you can see clearly that is the distance between the outermost electron as well as the nucleus is much higher. So what happens here? Here the force of attraction between the nucleus and the outermost electron is very less as compared to this. So we can easily remove this particular kind of electron. So here you can see that while moving in a particular group, the least amount of energy is required for the last member and the highest amount of energy is required for the first member present in a group. So while moving in a group, that is from top to bottom, the ionization energy decreases. So what happens as we move across a period? As you can clearly see, just for an example, if we move from beryllium to boron to carbon to nitrogen to oxygen to fluorine to neon. So here you can see a particular kind of trend, that is the ionization energy increases. So why the ionization increases as we move across a period? Because while moving across a period, the number of shell remains the same. What happens? Only one electron as well as one proton increases along with the neutrons, but the force of attraction between the nucleus and the electron keeps on increasing, and also there is a repulsion between some electrons. So we can see that the force of attraction is greater than the repulsion between the electrons. So in the case while moving in a period, the ionization energy increases with some particular exceptions. So what are these exceptions? You can clearly see that is the ionization energy for beryllium is higher than that of the boron, while the ionization energy of nitrogen is higher than that of the oxygen. So these are what? These are some of the exceptions. Otherwise, the trend for ionization energy moving in a period is increasing order. So moving and see the ionization energy for 20 elements, or we can say that from the hydrogen to the calcium. So this is a graphical representation where you can see these particular red dots. These are representing the energy or the first ionization energy in the kilojoules per mole. So you can clearly see, students, that is the amount of energy that is required to remove an electron would be much higher. So to remove an electron from the hydrogen atom, we would have required almost around 1250 kilojoules per mole. So here you can see that the ionization energy for hydrogen is around, that is between 1000 to 1500, that is around 1250. But the highest amount of but the highest ionization energy you can see is for the helium. For the noble gases, they are having the stable noble gas configuration, that is the 2,8. Here I am writing here 2,8, 2,8,8. So these are what? These are the stable configuration. It simply means that the argon, neon and helium are stable. They do not want to give an electron and want to accept an electron. So they simply don't want to lose their electron. But if we try hard and remove an electron from them, so we would have required much energy to do that work. So here helium is having the highest ionization energy, and as we move down in a group, that is in the noble gases, the trend for ionization energy keeps on decreasing. So you can see that in a particular period, just for an example, if I talk about from the lithium to neon, you can see the trend, that is the ionization energy keeps on increasing while we move in a particular period. As you can see here, that is from helium to neon to argon, the trend of ionization energy keeps on decreasing. So remember, students, this particular point, and you can clearly see that the ionization energy for beryllium is higher than that of the boron. This particular kind of questions, it is always asked in your examinations, as we know that the trend for ionization energy while moving across a period is increasing, but there is an exception for beryllium and boron and also for the nitrogen and oxygen. So you will get this reason when you will study this periodic table again in the class 11. So this is the one exception, this is the second exception in the second period. So there is also an exception, that is the magnesium and aluminium and phosphorus and sulfur. Remember, students, nitrogen and phosphorus, they are of the same group elements, and also beryllium and magnesium, they are also the same group elements. So the particular trend you can see and you can remember from these 2 points. So now, students, this is the ionization energy for 20 elements. So now we are going to see, that is the ionization energy for alkali metals. So for the alkali metals, that is the lithium, sodium, potassium, rubidium, cesium. So the trend for ionization energy is what? That is lithium having the smallest size. It is having what? It is having the large amount of ionization energy. And the cesium, which is having the biggest size, is having what? Is having the least amount of ionization energy. And you know that the alkali metals only have one electron in its outermost shell. So it is very keen to remove that particular electron in order to become stable. So here you see that the value for lithium, that is only around 525, and for the cesium it is only 374. So now, students, you have seen this particular kind of trend. So moving into what? That is the periodic trend in the first ionization energies, and you can see here that is we have plotted a graph up to 110 elements. So you need to remember this particular graph, and this is only for you to see that how the ionization energy keeps on increasing or decreasing while moving in a particular group or in a particular period. So here, students, you can see that while moving in a particular group, the trend for ionization energy keeps on decreasing, and also the noble gases have the highest amount of or the highest value of ionization energy. Why? Because they have the very stable electronic configuration, or I can say that they are stable in nature. They do not want their electrons to get disturbed or the electronic configurations to be disturbed. So here the trend for the noble gases is very much higher, and you can also see that for the alkali metals, that is from the lithium, sodium, potassium, rubidium, cesium and francium. Francium is a radioactive alkali metal. So in this case you can see that the francium and cesium are having the ionization value almost about the same. So in the particular alkali metal group, the lowest amount of ionization energy would be for the cesium. If I talk about with the francium, then the francium would be having the least amount of ionization energy in the group number 1, that is for the alkali metals. So now, students, moving to another slide and see that the lower the value of ionization energy, the more likely for it to be a cation, and higher the value of ionization energy, the less likely to be it or an atom to be a cation. And you can also see that the higher the value of ionization energy, it is more likely to form a cation, and the helium has the highest first ionization energy while the francium has the lowest value. You can clearly see they are at the extreme right. So helium is at the extreme right. So ionization energy while moving across a period increases. So helium is having the highest value of ionization energy, and also while moving from top to bottom, the ionization energy decreases. That's why helium is having the maximum value of ionization energy while the francium is having the least value of ionization energy. So now see this particular kind of trend in this particular. So here you can see that as we move across a period, what is happening to the ionization energy? It is increasing as we move from top to bottom ionization energy. So what happens if we move from bottom to the top? The ionization energy would increase. That's why the helium is having the maximum value while the francium is having the least value. So students, this is all about the ionization energy. So now moving into the next trend, that is the electron gain enthalpy. Moving into the electron gain enthalpy and electron affinity. So these are almost the same term, but there is a little much difference between these two terms. So what is the electron gain enthalpy and what is electron affinity? Electron affinity is simply the affinity for any atom of an element to attract a single electron in its gaseous state, while the electron gain enthalpy is the amount of energy that is released when an atom of any element gains a particular electron. So electron affinity is what? It is simply the tendency, or you can say that the attractability for any element. So how can you compare the value for hydrogen, for helium, for oxygen and for fluorine? Just for an example, if I say that no metals are deprived of electrons, they want the electrons to complete their octet and become stable. So how can you compare them? So for the comparing those values, you need what? You need a particular kind of value, that is in the terms of energy, or we can say that the enthalpy. So for determining the electron affinity for any particular element or an atom of an element, we need what? We need the term that is the electron gain enthalpy. So now you know the difference, that is the electron affinity is the tendency while the electron enthalpy is the amount of energy. So defining, that is electron gain enthalpy is defined as the energy which is released when an atom adds up an electron in the outermost shell when in the gaseous form. Remember students, we are going to talk about these two terms, that is the electron gain enthalpy and the electron affinity. So now you can also clearly see that the symbol for electron gain enthalpy is delta EGH. H stands for the enthalpy and EG stands for the electron gain. And the delta here, you can see here, this is the change. So this is a change in the energy when an electron is gaining. So students, moving into another, that is the electron gain enthalpies examples. Here you see chlorine, which is what? Which is a non-metal. So non-metals are what? Non-metals are deprived of electrons. So when we give this one electron to this chlorine atom, when it is in the gaseous state, it forms chloride ion. And in the process of formation of chloride ion, it removes certain kind of energy. So what is the value of that energy? That is 349 kilojoules per mole. And since this particular kind of energy is removing, or it is removed, so we can say that this particular energy can be represented like the amount of energy that is released, that is with the help of this negative sign. So here you see, to represent the electron gain enthalpy, we uses what? We uses certain kind of symbols. Just for an example, this is the energy which is being released. So if the energy is releasing, coming out of the system to the surrounding, it means that we have to provide what? We have to provide a negative sign. And just for an example, if I add up an electron to any element, just for an example, a metal, it would do what? It will not remove as much that energy as it is required for the non-metals. While in some cases, the electron gain enthalpy would be positive. It means what? That for an addition of an electron, we would require a large hell amount of energy. And you can also see that for the noble gases, which are having the stable noble gas configuration, to add up an electron to the noble gases, we have to provide the energy. It simply means that the electron gain enthalpy for the noble gases would be a positive value. So here you can clearly see and you can know that this negative sign represents that the energy is being released. And here you can see the value, that is 349 kilojoules per mole for the chlorine atom. And remember students, that the chlorine is having the highest amount of electron gain enthalpy in a whole periodic table. So this is a question that would have always asked in your examinations, that which particular element will be having the highest amount of electron gain enthalpy. So the chlorine atom or the chlorine element will be having the highest amount of electron gain enthalpy. So moving into another, that is the oxygen. So when we add up an electron to the oxygen atom, when it is in the gaseous state, it forms an oxide, and the amount of energy released is termed as the delta EGH1, or simply electron gain enthalpy first. Here you can see the number of protons that are present in this particular oxygen atom is 8, which is also equal to the number of electrons. So here this particular atom is electrically neutral, while in this case the number of protons are what? They are somewhat less than that of the electrons. So here the number of electron is what? The number of electron is 9, while the number of proton is only 10. So what happens when we gain one electron and when we give one electron to this particular anion? Would it give the same amount of energy, or will it release any kind of energy? So let us see that. So when we give one more electron, so what happens here? There is a lots of repulsion between these particular electrons. So what happens when an incoming electron comes to O minus? The electrons that are present in the shells, they repel that electron. It means that we have to provide an extra amount of energy to fit that particular electron in the outermost shell. So when this particular electron comes in the outermost shell of this O minus, it would form O2 minus, and here you can see that it is represented with the minus energy sign. It means that we have provided this energy to the reactant side. So what are the conclusions that you draw from here? That is, the first electron gain enthalpy can either be positive or negative depending upon the nature of the element, but the second electron gain enthalpy is always endothermic. Why? Because there is a repulsion between the electrons and it repels the incoming electrons. So we would require an extra amount of energy to put in. So for that the electron to get fitted in the outermost shell. So remember students, that is delta Eg1 for any element, it could either be positive or negative depending upon the nature of element, while the successive electron gain enthalpies are always positive. So moving into another, that is the units of electron gain enthalpy. So here you see that is the kilojoules. So here you see that is the kilojoules per mole, or you can either use electron volt per atom, same as that in the case of ionization energy. So now moving into another and see here, that is what happens when we give an electron to the fluorine atom. So when we give an electron to the fluorine atom, some kind of energy is being released, and also students see the difference in the sizes. This is the fluorine atom whose size is like this, and when an electron comes into the outermost shell of fluorine, its size becomes somewhat bigger. So this is what, this is an anion, and this is what, a parent atom. And you know that you have studied in your previous lecture, that is the size of anion is always greater than that of the parent atom. So moving into another and see the variation of electron affinity or the electron gain enthalpies in a period. So here you see some of the elements along with the values. So what happens, that is the value for hydrogen is -73 and the value for helium is greater than 0, or you can see that for all the noble gases the value for electron gain enthalpy is greater than 0. It simply means that we have to give an extra energy and put some extra amount of efforts for these particular elements to gain an electron. And you can also see that is the particular value for lithium, that is -60. For beryllium it is greater than 0. For boron it is -27. For carbon it is -122, and for nitrogen it is a positive value. For oxygen it is -141, and for fluorine it is -328. So what is happening here, as we move across in a period, the electron gain enthalpy is increasing, but it is not a particular kind of trend, as it is having some kind of exceptions. But you can see apart from these exceptions, just like for beryllium and for nitrogen. So you can see that for the lithium, carbon, oxygen and fluorine, the electron gain enthalpy keeps on increasing while we move down in a group. So what happens to the electron gain enthalpies? You can clearly see here that students, while we move down the group, the electron gain enthalpies keeps on decreasing. Why it keeps on decreasing? Just remember students, if this is what, this is a particular atom or the first member of the group, and this is what, this is the last member of the group. This is the nucleus, this is the nucleus, and this is the size. So what happens here, you can clearly see that is the distance between the nucleus and the outermost shell is less in the first member, while it is more in the last member. So when an electron comes in the outermost shell, the nucleus which is present here should be able to attract that electron. So what happens, if the distance is much larger, the attractability would be much less. That's why while we moving down in a group, the electron affinity values goes on decreasing. But there is an exception. You can see that for this particular second period and the third period, the successive or the first electron gain enthalpy is somewhat greater. That is, for fluorine and for chlorine, the value of electron gain enthalpy for chlorine is higher than that of the fluorine. You can understand it while see this in a graph. That is, while moving across a period, the electron gain enthalpy goes on increasing, or it keeps on increasing, with the exceptions like beryllium and nitrogen. Getting? While moving down a group, that is from top to bottom, here you can see clearly that is for fluorine, chlorine, bromine, iodine and astatine, that is the trend is somewhat goes on decreasing, but chlorine is an exception which is having the highest amount of electron gain enthalpy, or we can say that this is the electron gain enthalpies for the second period and the third period. There is a difference, or there is an exception. So the electron gain enthalpies for the third period is somewhat higher than that of the electron gain enthalpies for the second period. So this is generalized form, and you can remember that while moving in a period, the electron gain enthalpies increases from left to right, while moving down the group, the electron gain enthalpies decreases. So this is all about electron gain enthalpies, and we are going to see some of the values in a particular chart so that you can remember these values. So here you see that these are fluorine, chlorine, bromine and iodine. So here, remember students, which would require more amount of energy. So remember students, which element is so much deprived of electron and which element requires an electron at any case, that is the halogens. They are only one electron less than forming the octet or simply forming the noble gas configuration. So they are so much in attraction with the electron that if we give one electron to the halogens, they will give large amount of energy. You can clearly see that this negative sign is showing the amount of energy released and this positive sign is showing that the amount of energy that we need to give. So here there is a particular line, you can see that. So the elements that are coming down this line, it means what? That we have to provide an extra energy for the electron to get fit in their outermost shell, in their gaseous state. While in the case the energy is having negative values, the amount of energy is being released. So the highest amount of energy is released in the case of halogens. You can clearly remember this point, and you can see that there is an exception just for like nitrogen, beryllium. Below nitrogen we comes the phosphorus and below beryllium we get the magnesium. So these are some of the trends. So students, you need to take a look to this particular graph and see the values of electron gain enthalpies. Getting students? Now moving into the next, that is the periodic trend in the electron affinity. As you know, we have already discussed that while moving across a period, electron gain enthalpy goes, or the electron affinity goes on increasing, while moving down the group it goes on decreasing. So now students, it's time for us to move into the next, that is the electronegativity. So what is this electronegativity? So electronegativity is a measure of tendency of an element to attract the bond pair of electron towards itself. And from where should it attract? It is attracting in a covalently bonded molecule. Just for an example, if I say HCl, so hydrogen and chlorine, they are forming what? They are forming a covalent bond. So the chlorine is attracting the electron towards itself. It means that the chlorine is having what? Chlorine is having the higher amount of electronegativity than the hydrogen atom. So this so here you can see that ionization energy and electron gain enthalpies, these can be measured, while the electronegativity, it is simply the measure of tendency, so it cannot be measured. But we have a scale that is given by Pauling, so we call it a Pauling scale and Mulliken scale and also Allred-Roschow scale. But the most correct and the precise scale is Pauling scale. So for the Pauling scale, the value for fluorine is assigned to 4, and in comparison to fluorine we have assigned the values to some other elements. So let us see what are those values and what is the order of electronegativity for the elements that we come across in the examination. So remember students, that is fluorine, oxygen, nitrogen. So the highest amount of electronegativity is used for the fluorine, that is it is having the value of 4.0, or you can simply remember that FON, that is phone. So the highest amount of electronegativity value is used for the fluorine element. So as we move from fluorine, oxygen, nitrogen, the value of electronegativity keeps on decreasing, that is 4.0, 3.5, 3 and approximately equal for chlorine, that is 2.9. So chlorine and nitrogen, they are having almost equal electronegativities, and from chlorine to bromine the electronegativity decreases. So here while moving from chlorine to bromine, electronegativity decreases, while moving from bromine to iodine, electronegativity also decreases. And you can see that from iodine, sulfur and carbon, the electronegativity for all these three elements is almost or approximately the same value, while the electronegativity for phosphorus is somewhat less than that of the carbon and hydrogen. In all these cases, in the cases of these known metals, hydrogen is having the least amount of electronegativity. So it simply means, students, you can see here, if I say that HCl, so HCl is what? Hydrogen chloride or hydrochloric acid. So what happens in this HCl? Here this HCl is formed by the sharing of one electron from hydrogen and also one electron from chlorine atom. So here you can see a bond. This bond here is termed as the covalent bond. So what happens when the electronegativity of chlorine is higher than that of the hydrogen? So this particular electron which is shared mutually between the hydrogen and chlorine is now being pulled towards the chlorine. So it will form what? It will form like this, and the electrons that are present here would be pulled towards the chlorine like that, due to which it would acquire some kind of partial positive charge and it would acquire some kind of partial negative charge. So here you can clearly see, since the electronegativity of chlorine is higher than that of the hydrogen, that's why chlorine is able to pull the electron or pull the covalently bonded electron towards itself, and it happens only in the covalently bonded atom. And what is a covalent bond? Covalent bond is that type of bond which is formed by the mutual sharing of electrons. You should need to remember this particular point because you have already studied in your class 9, and I have already told you in the previous chapter, that is chemical reactions and equations, in detail. So students, moving and see the value of electronegativity for the whole elements present in the periodic table. So here students, you can see clearly, that is the electronegativity for the fluorine is the highest, that is having the value of 4. So while we move across from right to left in a period, we get the lower value of electronegativity, and while we move from top to bottom, we get the lower value of electronegativity. So it is simply the attractability, or I can say it is simply the measure of tendency to pull the electrons. And which element will pull electrons? The non-metals will pull electrons more efficiently as compared to the metals and also as compared to the noble gases. So you know that the highest value of electronegativity will be for the fluorine or the halogen element. So here the fluorine is having the highest value of electronegativity, and the trend, you know that for after fluorine, the oxygen and nitrogen is having the lower values, and also the chlorine is having the value approximately equal to that of the nitrogen. So this is particular value. You can clearly see that hydrogen is here, and the whole value for the electronegativity is used for the non-metals. So non-metals is having specially some kind of particular value for electronegativity. In the case of metals, they do not attract electrons, they simply want to lose electrons, so they are having very less value. So I hope students, you get a better idea about the ionization energy, electron gain enthalpy and electronegativity. So now moving into the electronegativity of elements, you can see the trends, that is while moving across a period from left to right, electronegativity increases, and while moving from top to bottom, electronegativity decreases, or I can simply say while moving from bottom to the top, electronegativity value goes on increasing. So here you can see, the higher the number of electronegativity, the more likely for it to attract the electrons, and we have measured this on the basis of Pauling scale. So moving into another, the nature of oxides. So what are oxides? Oxides are the compounds that are formed with the oxygen. Just for an example, when metal combines with oxygen, it forms metallic oxide. Just for an example, I have written here sodium, when it is combining with oxygen, it is forming what? Na2O. So this is what? This is an oxide of metal, or I can say this is what? This is a metallic oxide. So it is formed when metal reacts with the oxygen. And there are also the non-metallic oxides. So what are the non-metallic oxides? The non-metallic oxides are those when a non-metal reacts with oxygen. Just for an example, you can see when hydrogen reacts with oxygen, it forms H2O. So here this H2O is what? This H2O is non-metallic oxide, and other non-metallic oxides are like CO2, SO2, NO2, P2O3, P2O5. So these are what? These are the non-metallic oxides. So what is their nature as we move across in a period from left to right? So while moving from left to right, you have clearly seen that on the left side we came across the metals, while as we move from left to right, we move towards the non-metals. So metals are forming metallic oxides while non-metals are forming non-metallic oxides. And the nature for metallic oxides are what? They are strongly basic, and as we move further, the basicity decreases and the oxide becomes acidic in nature. And in somewhere between, we came across the amphoteric oxides. So what are these amphoteric oxides? Amphoteric oxides are those oxides which reacts with bases as well as with the acids. So these are termed as the amphoteric oxides. We are going to deal with these acidic oxides, basic oxides, amphoteric oxides, neutral oxides in the chapter acid, bases and salt. So students, what happens when we move across in a period? The nature of oxide changes from basic to the acidic. And what happens when we move in a group? The basic nature keeps on increasing, because as we move from top to bottom, the tendency for an element to remove an electron also increases. It simply means what? It simply means that it has a more tendency to become a cation, and higher is the tendency to become a cation, higher will be its basic nature. So this is the nature of oxides that we have seen, and this is what? That is the periodic properties. So for the periodic properties, you can see, students, what we have discussed, that is the metallic character. So what happens to the metallic character as we move from top to bottom? This is top and this is the bottom of a periodic table. So if we move from top to bottom in a periodic table, the metallic character increases while the non-metallic character decreases. And what happens when we move from left to right in a periodic table? The metallic character decreases and the non-metallic character increases. And checking for the electron affinity or the electron gain enthalpy. So what happens when we move from left to right in a period? So it increases, while moving from top to bottom it decreases. Talking about the ionization energy, it is having the same trend, that is, while moving from top to bottom in a group it decreases, and moving from left to right in a period it increases. Same is the trend with the electronegativity. Same is with the electronegativity, that it goes on increasing when we move from top to bottom, when we move from left to right in a period, and top to bottom in a group it decreases. Remember students, all these are having some kind of exceptions. So the exceptions are the ones that you need to remember. Talking about the valence electrons in a period increases by 1, while when we move across a group they remains the same. Talking about the electron shells, so the electron shells, or simply the shell, they remains the same while we move across a period. While we move down from top to bottom in a group, the shell keeps on increasing by 1. So here you have seen and revised all the periodic trends that we came across in our chapter, and also from this you can see that the atomic sizes would be increasing or decreasing depending upon the shells and the electrons being added. So students, this is all for today. We will meet you in the next class with some questions of the module discussions. So till then students, thank you all, and that's all for today.